Okay, here we go again, Chemistry 3202 review. Looking at Unit 4, Section 1 here, defining oxidation numbers, or more correctly, I guess, defining oxidation states. In the last lesson, we were looking at oxidation reduction, and we said Leo is an oxy. He's pretty mad there in this picture. But loss of electrons is oxidation. And when we looked at the last examples that we did in the other lesson, we were looking at simple things like sodium going to sodium 1+, so we knew that it was losing 1 electron. Or aluminum going to aluminum Al3+ going to aluminum, which means it would have to gain 3 electrons to do that. That was easy enough to visualize, I guess, what's going on there with the Lewis dot diagrams. But what we want to be able to do is we want to be able to assign oxidation states to just about any species that we have, to be able to do a real quick look and say, you know, is anything changing? Is there anything here that gained electrons? Is there anything here that lost electrons in a chemical reaction? So we want to be able to look at the chemical formulas and quickly and easily define what their oxidation state is. Are they in a state where they have extra electrons, or are they in a state where they have fewer electrons? All right, so let's have a look at it. And this is dealt with on page 721 of your textbook. And there's a few questions here, so you might want to try some of these and fire them off to your online tutor or check the answers in the back to see if you can do these. So let's have a look. Here's the outcomes. Okay, so the very first thing we're going to look at is saying, well, what is an oxidation number or an oxidation state? And in terms of this, it's just a way of looking at an atom that's in a molecule and say, you know, what's its current state in terms of the number of electrons. If we were to do a Lewis dot diagram, which one would be attracting the electrons the strongest? Which one would be in a gaining of electron situation? Which one would be in a loss of electrons? So it would be a hypothetical charge, so to speak. It's not really a charge. It's just going to be a state. Don't think of it as a charge like an ion, like sodium ion. That would have a charge of +1. What we're simply looking at is a state. So let's look at a couple of examples to see if you can pick some sense as to what we're talking about. Okay, so we're looking at this and we're saying, all right, if we do a Lewis dot diagram for water, all right, we know that oxygen has 6 electrons. We know that hydrogen has 1 electron, and therefore the oxygen and hydrogen are going to form a covalent bond. So let's move these guys together. So we move them together, and there we go, we form the covalent bonds. And we'll take this guy now and we'll move up and we'll form a covalent bond. Now, the thing with this covalent bond is that it's not equal sharing, is it? Because if we consider the electronegativity values, their attraction for electrons, remember Chemistry 3202, right? Oxygen has a very high electronegativity, 3.5. Hydrogen has a low electronegativity of 2.1. Even though these electrons are being shared between hydrogen and oxygen, they're not being shared equally. And as a result, we could say that the water molecule is going to be polar towards the oxygen. So in other words, the oxygen is really pulling the electrons closer to itself and further away from the hydrogens, because the hydrogens are really not strong enough to attract those electrons. Now, they're not losing the electrons, are they? It's just that the oxygen is attracting them much more strongly than the hydrogen. It's not a transfer of electrons. It's still covalent. It's still sharing. So these bonds here are still shared. The problem is it's not equal sharing. They're being pulled closer to the oxygen and further away from the hydrogen. So we're looking at this and we're saying, okay, if oxygen comes with 6 of its own electrons and it's attracting these 2 more strongly, then can't we say that it's somewhat in a state where it's attracted to electrons? So we can say that oxygen is in a state where we would say it would be like in a -2. It's attracting 2 extra electrons that it normally wouldn't have. So we would refer to the oxidation state of oxygen as -2. It's got 2 extra electrons. Each hydrogen, therefore, if oxygen is attracting this electron, that means this hydrogen is losing its electron. So we would say that each hydrogen would be in a +1 state. Not a charge, but just a state. All right? Okay, so -2 for the oxygen. Each hydrogen is going to be in a +1 state, which is going to cancel out the negative there. So let's have a look at some more of these. So we're saying that since the water has the stronger electronegativity than hydrogen, not water, Okay, let me see if I can't fix that up for you. Okay, so the oxygen has a much stronger electronegativity than the hydrogen. Here we go. We can say that the oxygen owns the electrons in that polar bond. All right, it's attracting it more often. We would refer to it as a bond dipole, and therefore we would state that oxygen would be in a 2- state. Okay, let's look at another one here, and we'll say, okay, let's look at chlorine. Now, in a chlorine molecule, we can do the Lewis dot diagram, but because their electronegativities are the same, the electrons are equally shared, 50-50. So they're not closer to one chlorine than the other, like it was with oxygen and hydrogen. They're equal sharing, so what we can say is that if they're sharing that bonded pair of electrons, then we would say that its oxidation state is 0. It came with 7, and it still has 7 of its own strongly attracted. The pair of electrons is not attracted to one or the other. They're equally shared, so we would say that neither one of them is pulling the electron. So they have an oxidation state of 0. Okay, let's look at another example. Let's look at the NH3 molecule. Now NH3 would have a Lewis dot diagram that looks something like this. And we know that the electronegativity of nitrogen is going to be 3.5. 3.0? Let me just check the periodic table to make sure. Okay, 3.0 for nitrogen. So the electronegativity of nitrogen is 3.0, and hydrogen would be 2.1. So this is very much a polar bond. So we're seeing this charge separation here only in polar bonds, and we're seeing that the nitrogen now is attracting these electrons. It's attracting the electron from this hydrogen, it's attracting the electron from that hydrogen, and it's attracting the electron from that hydrogen. So in a sense, once again, if we want to look at this and say ownership, even though they're sharing, the nitrogen really has ownership over these 8 electrons. It's got 5 of its own, and it's attracting 3 others. So in this particular example, we can say that nitrogen would be in a -3 state, and hydrogen would be in its characteristic +1 state. Hydrogen is very weak. Anything that hydrogen's bonded with, generally hydrogen gives its electrons up to. It's a very weak atom, 2.1 electronegativity. So because nitrogen is stronger, it's attracting the electrons, it's attracting 3, hence a -3. Hydrogen is losing its electron +1. And because we've got 3 hydrogens, then that's going to cancel out. 3 hydrogens, 3 plus, 1 nitrogen, -3. Therefore, it's not a charge, it's not a charge. It's simply an oxidation state. Okay? Some of these guys are really not always that easy or easy to identify. So what we want to be able to do, we want to be able to recognize if any oxidation and reduction occurs. And in order to do this, we want to be able to quickly and easily look at these oxidation states to see if there is any change in the electron numbers. And a way we can do this real simply is there's a table on page 724 of your text, table 18.1. And what it does is it summarizes some of the characteristics of the different species that we would use and what their oxidation state would be. So remember now, elements like chlorine, they're equally sharing, so they would not have any equal pull. There's no bond dipole, they're nonpolar. There's no pull between the 2 chlorines, therefore oxidation number of 0. Any of the monoatomic ions like sodium ion, their oxidation state is going to be their charge. So for instance, sodium loses 1 electron to become sodium 1+, therefore it's in a state of 1+, it's lost its electron. Aluminum has 3 electrons, it loses them to be Al3+, therefore the state for aluminum is 3+. Copper has 2 possible states. Copper could lose 1 electron to be copper 1+ ion, or it could lose 2 electrons to be copper 2+ ion. So whatever the charge is on the simple ions, that's going to be their oxidation state. Now when I mean simple ions, I mean monoatomic, sodium, aluminum, potassium, iron. When we think of complex ions, we think of carbonate, phosphate, PO43-. They're different. All right, so these are the simple monoatomic ions. So whatever their charge is, that's their state. Anytime oxygen is bonded, that's the key word there, bonded, because when it's by itself, it's going to be 0. But when it's bonded, it's always going to be the substance that has the highest electronegativity, 3.5. So anytime it's making a covalent bond, it's always going to be the one that attracts the electron. So oxygen is always going to be -2. It's got 6 electrons. It needs to make 2 bonds. It's so strong it attracts those 2. So -2. The only exception here is when it's in peroxide, hydrogen peroxide, in which case it's going to be only a -1 state. All right, that's the only exception. Hydrogen, because hydrogen is so weak, it has a very low electronegativity. Hydrogen's generally going to be +1. It's always going to lose its 1 electron, except when it's bonded to metal, something like sodium hydride, in which it's got no other choice but to be a negative, because remember, sodium has a very low electronegativity, 0.9. It's going to give up its electron anyway, so it would give it up to hydrogen in that case. So hydrogen would gain 1 when it's bonded to metals, like sodium hydride, potassium hydride, things like that. They're rare. All right. Generally speaking, hydrogen when bonded is going to be +1. Fluorine. Fluorine is one of these special ones here. It has the highest electronegativity of all atoms on the periodic table. Fluorine is 4.0. Whenever fluorine is bonded to anything, it's always going to strip away that electron. It's always going to be -1 because fluorine is so strong. And last but not least, if we have 2 things that don't fit the categories up above, like say we had a bond between phosphorus and nitrogen, or phosphorus and say chlorine, we have to look at each one of these and say whichever one has the highest electronegativity from the periodic table, whichever one was the strongest of the 2, that's the one that's going to attract the electrons. And the highest electronegativity is going to be the one that's negative. That's why oxygen was always -2, because it was always the strongest. That's why fluorine is always going to be -1, because it's the strongest. Hydrogen is always going to be +1 because it's the weakest. All right, so we'd have to compare the electronegativity. So let me do a few examples here. Here's an example. The first one, we look at bromine, Br2 liquid. Well, we have to identify the compound. First off, we know that bromine, Br2, is a halogen. That's how bromine exists in its elemental form. So because it's an element, it's going to have an oxidation state of 0. We don't have to do Lewis dot diagrams. We don't have to do none of that. We're simply looking at this and saying it's an element. It's an element. Elements are always 0. So the oxidation state of bromine is 0. And what I like to do is I like to write a little 0 up above. That's my little note to say that bromine is 0. Okay, the next one, along the lines, we're looking at water. And I'm looking at water and I'm saying, okay, no problem. I'm looking at my table up above and I say oxygen is bonded here, so that's going to be -2. And I don't know what hydrogen is, so I'm simply going to do something like this and say there's 2 of them, so it's going to be 2 times x, which equals plus a -2, which equals a 0 charge. So 2x equals +2, so x is going to be +1. Well, that's what the table told me up above anyways. It's going to be +1. But what I'm doing here now is setting you up for something bigger. A little bit of mathematics there. Okay, let's look at ammonia, NH3. Okay, we're looking at ammonia, and I'm looking at this guy and I'm saying, okay, I got bonded hydrogen, so that's always going to be -1. So now I want to figure out what nitrogen is going to be. So I'm going to do my little math. I'm going to say nitrogen, there's only 1 of them, so I'm going to call that X. But I've got 3 hydrogens, +1, sorry about that. Hydrogen's always +1, which has a net charge of 0. So X plus 3 equals 0, so X. The state of nitrogen is going to be -3. Now what am I doing here? Well, that next little statement here is saying no matter what the states are, the net charge must balance out. So in this case I said water has a charge of 0. It doesn't have any charge. And what I'm trying to do is balance out the states here and saying, well, if oxygen is -2, then hydrogen had to be +1 each. +1 each. 2 times +1 is +2. +2 and -2 cancels out. Same thing's true here. NH3 has a 0 charge on the molecule. So if hydrogen is +1 and I've got 3 of them, and that's 3 plus, so the nitrogen must be minus 3 in order to cancel it out. Well, what happens if we had a complex ion where we had a charge involved, something like carbonate? Well, same thing applies. What happened here? That's supposed to be CO3. Same thing applies here in this case. We're saying, okay, oxygen is going to be minus 2. I don't know what carbon is. So I'm going to call this guy X. And I'm going to say, well, that's going to be 3 times the oxygen, which is minus 2. And there's going to be a minus 2 left over because of the charge here. Carbonate has a 2 minus charge. So when I add up my positive and negative states, I should be left with 2 left over, negative 2 left over. So let's solve it. And we say the charge on carbon, or the state of carbon, sorry, is going to be a minus 6 equals a minus 2. So carbon is going to be plus 4. Is it not? Plus 4 and a minus 6 is equal to minus 2. There we say we've got carbon, which is going to be in a state of plus 4. Let's try a couple more of these. Okay, here's a couple more. Hydrogen iodide. Well, we know what hydrogen is. Hydrogen is going to be a plus 1. So right off the bat, we should know what iodine is. Iodine is going to be minus 1. I didn't have to do any math to figure that out. Okay, what about oxygen? Well, oxygen O2 is in its element form, so it's going to be 0. Doesn't have a state. Well, it does have a state. It's in a state of 0. It's neither lost nor gained. It's equally shared. Okay? In the case of PCl5, now this guy is a little bit more difficult because we don't know anything about phosphorus, we don't know anything about chlorine, so we'd have to do the Lewis dot diagram, or at least consider the electronegativity values here. And let me show you what we mean by considering electronegativity values. If I was to do a Lewis diagram of phosphorus, phosphorus would be the central atom. It's going to have 5 electrons. And I'm going to start filling in the chlorines around it as we go. 1, 2, there's another one. Chlorine can only make 1 bond, you see. Now phosphorus does something here called hybridization. Because it's down in the 3rd energy level, it's capable of making more than 3 bonds, right? So what's going to happen here, don't worry about this. You're going to see that chlorine is going to come in here and make a bond with that electron and then this electron right here. So we see 5 bonds happening with the phosphorus, which is allowed because phosphorus, again, is one of these low molecules. Don't worry about it. But what we're saying then is, what's happening to the attraction of these electrons? Well, we'd have to consider the electronegativity of chlorine, which is going to be 3.5 for its electronegativity. Let me type that in so it's a little more clear. Okay, so the electronegativity of chlorine is 3.5. Phosphorus's electronegativity, I don't know what it is. I can't remember that. So what I do is I consult my periodic table. Phosphorus has an electronegativity of 2.1. That's pretty weak. So the question is, these electrons are being attracted to the chlorines. So if chlorine is attracting, it can only attract 1 electron, can it? If I look at this chlorine right there, there's only 1 electron involved in the bond. So this chlorine is attracting that electron. So that chlorine is going to be in a state of minus 1. So what's going to be the state of phosphorus? Well, phosphorus is going about this 5 times with the chlorine. So every time, phosphorus is going to lose to chlorine because chlorine is stronger. So if chlorine does this 5 times, that means phosphorus is going to lose 5, which means phosphorus is going to be in a state of plus 5. It's still in a covalent bond, but its electrons are being attracted more strongly to the chlorine. Okay? We look at electronegativity values. Did I have to do the Lewis dot diagram? Absolutely not. I know that because chlorine is the strongest of the 2 and that chlorine can only make 1 bond anyways, that chlorine is going to attract each time. So it's minus 1. Okay, there we go. Let's try a couple more of these. What about HCN? Well, this is a situation where we got HCN here, and here's the Lewis dot diagram. Let me just cover up this on the bottom. We've got carbon that has 4 electrons. Hydrogen makes 1 bond with it, and we're getting a triple bond here with the nitrogen. Now, nitrogen is the stronger of all of these. So of these triple bonds that are forming here, all of these electrons are being attracted to the nitrogen. So in this case, the nitrogen brings 5 and it's attracting 8. So nitrogen is going to have a -3 state. We know that hydrogen is weak to start with, so hydrogen is going to lose its electron or be less attracted to hydrogen than it is carbon. Now, carbon is special here, so we know that hydrogen is going to be a +1. So what's going on with the carbon? Well, we can do the math here if you want to figure out carbon, or we can go through it logically in our head. Let's do the logical step first. All right, carbon brings 4, but it's only leaving with 2. It's not leaving anywhere, but you know what I'm saying? It brings 4 to the bonding, and it only has control over 2. So brings 4, control over 2. That means it lost 2. So carbon should be in a +2 state. Does that make sense? +2 + 1 is +3. Nitrogen is -3. There's no charge on HCN. Looks good to me. Or you could do the mathematical approach here and saying, okay, hydrogen we know is +1 because it's bonded. We don't know what carbon is. We just found out what nitrogen is. It's -3 because it's the strongest electronegativity. The 3 doesn't come from this. The 3 comes from the fact that nitrogen can make 3 bonds. So it's going to attract those 3. And then we do our math here and we figure out that, yeah, lo and behold, it's +2. Let's look at another one here, sulfate. All right, what do we know? Oxygen, -2. Can we take away from that? Absolutely. We know that if that's going to be -2, then the sulfur, we have no idea what it is, but we can figure it out. And as we go down through this, we can see that I just moved all of that there. Then let me just move that up. There we go. Sulfur is X. Oxygen is 4 times -2. We got 2 left over. So what we're going to see here is X -8. Therefore, the charge on sulfur is going to be +6. Okay, not the charge. I just said it again, didn't I? It's not a charge. It's a state. It's the fact that it's losing its electrons to oxygen. Oxygen is more strongly attracted. Let's look at sulfite, SO3. Now, you might say, well, you know, we're dealing with oxygen, we're dealing with sulfur, the charge is the same, but we only got 3 oxygens this time. So in this case, the oxygen is still -2. And when we look at this, we don't know what sulfur is, so we're going to call sulfur X. Oxygen is -2. We're going to multiply the oxygen by 3, because we got 3 of them. We got a -2 left over. Therefore, the state of sulfur in this case, when we do our little bit of math here, is that sulfur is in a +4 state. Ha! If we had sulfur involved in some kind of chemical reaction where it started with sulfate and ended up with sulfite, we'd know that something redox just happened here because it would have gained 2 electrons. It went from a +6 state, picked up 2 electrons, to be now in a +4 state. So if we've seen that in a chemical reaction, we could quite quickly say that's a redox reaction. There's electrons being transferred. We can see it in the sulfur. All right? And that's the purpose of doing this. Here's a couple more examples. Chromium. This guy is a little bit different because now it's got 2 dichromate. Sorry, it's got 2 chromiums here. What do we know? Well, we know the oxygen, -2. You do the math on this. In this case, we don't know what the chromium is. And we got to say, well, we got 2 of them. We got 2 of these guys, so it's going to be 2 times X this time. 7 times -2, and we've got a 2 charge left over, -2 left over. We do our math here, and we realize that chromium is in a +6 state. Each chromium is in a +6 state. Over here, we're saying, is there any difference? We got Cr2O7 here. Here we got CrO4. Is there any difference in the oxidation state? Well, let's look at it. Once again, what do we know? Oxygen, -2. Chromium, we're going to call X. So it's going to be 4 times -2 is -8 with 2 left over. So chromium must be in a +4 state this time. What did I do there? Obviously, I did something wrong. I can't do simple math. Okay, 4 times 2 is 8, not 6. Let's try this again. 4 times minus 2 is minus 8. So therefore x is equal to minus 2 plus 8. So x is equal to plus 6. So in this particular case, we can say there's lots happening, but whatever it is happening is not redox because the chromium did not change, the oxygen did not change. Even though it looks like something serious happened here, which it probably did, some kind of chemical reaction happened, but it was not an exchange of electrons. So therefore it's not redox. Likewise down here we're saying, okay, hydrogen is always plus 1, therefore chlorine is going to be negative 1. Now in the case of barium hypochlorite here, perchlorate, sorry, it's an ionic compound. So the easiest way I find to do these guys is let's take this ionic compound and separate it into its component ions. So what's really going to happen here is this guy is going to break apart into a barium ion and 2 chlorate ions, like this. So I'm going to look at this and say, well, if this is going to break into its ions, I know exactly what the state of barium is now. Barium is going to be plus 2. Okay? So barium is going to be plus 2 because it's a simple ion. Oxygen is going to be minus 2. And you notice how these 2's are going to start interfering here? I'm not going to do it like that. I'm going to break this down and say whatever chlorine is in this ion, it's going to be the same thing here. So what I'm going to simply do is figure out the oxidation state of one of these, and then the chlorine is going to be the same thing. So in this case, the oxygen is going to be minus 2. And that's going to make it what? Okay, do this in our head. 2 times 2 is minus 4 with 1 left over. So we want to take care of a minus 3. So chlorine must be in a plus 3 state in this case. And we do the math, and there you go. So chlorine is in a plus 3 state. All right, so that's the easiest way to do those complicated ones. Break them down into their ions and then do each ion separately. Okay, here's a typical example that you might be asked to do on a public exam. It might say, you know, here's 4 equations. Which equation represents a redox reaction? So here I've got 2 equations. I'm saying one of these is redox and the other is not. Prove it. All right? Well, what we have to do here is we're going to look at each of these and go through each one. So let's start with methane, CH4. I'm looking at this and I'm saying, okay, bonded hydrogen, that's going to be plus 1. So it should be obvious now that carbon is going to be plus 4 in that state. Okay, chlorine is an element, so that's going to be 0. In the case of HCl, we know that hydrogen is going to be plus 1, which makes chlorine negative 1. All right, looking at this so far, the hydrogen did not change. It's plus 1 before, it's plus 1 after. Ooh, look at that. Chlorine changed. Chlorine went from 0 to minus 1. So it looked like the chlorine gained an electron. What's going on right here? Well, this is one of these Lewis dot diagram things, but you don't necessarily have to do it because we're looking at this and we're saying, hey, chlorine is the strongest of all these guys. Chlorine has an electronegativity of 3.5. So in this sense, chlorine is going to gain that electron, so it's going to be negative 1. We know that hydrogen is the weakest, so it's going to be plus 1. What's going to be the state of carbon? Well, you can do this in your head if you want. 3 times plus 1 is plus 3 minus 1, so it's minus 2. So we want to cancel that out, so the carbon has to be plus 2. Do we have redox? Yes, this is redox. Because we know that the carbon went from, see what I've done? I got the wrong charges there. You guys got to help me out. Carbon went from minus 4 to minus 2. I got the wrong charges, right? 4 plus, in order to cancel out 4 plus, I need 4 minus. Right here, 3 plus, 1 minus, I'm left with 2 plus, so I need minus 2 to cancel that out. So carbon went from minus 4 to minus 2. Well, what did it do? It lost 2 electrons. It had 4 electrons, now it's only got 2. It lost 2 electrons. What else changed here? Because we've got to have reduction with oxidation. We can't have one by itself. We have to have both processes. In this case, we've got the chlorine going from 0 to minus 1. So it went from no electrons to having an extra 1. So it's going to be a 1 minus. That's reduction. So yes, this is redox. Let's look at the next example here. PCl3 plus 3H2O going H3PO4 and 3HCl. See if we can do this one right now. PCl3. Well, we know chlorine has the strongest electronegativity, so chlorine is going to be -1. It has 7 electrons. It attracts 1. It does it 3 times. So that means phosphorus is going to be +3. Okay, good enough. Oxygen is -2. That makes hydrogen +1. Don't worry about the 3 in front. That means nothing. Not in terms of redox for now. H3PO4, well, the oxygen is -2. The hydrogen is +1. I think I got to do some math on this one. Okay, let's do some math on this one. And we're looking at this guy, and I'm going to call this 3 times +1 plus x. And that's going to be 4 times -2. So that's going to be equal to 0. So we've got x plus 3 minus 8 equals 0. So x is going to be +5. Did the phosphorus, oh yeah, phosphorus went from +3 to +5. Now what we got to do is see if there's any other changes here. Hydrogen is +1, which makes chlorine -1. Okay, is this redox? And the answer to that is, be very careful, phosphorus went from +3 to +5, so it was deficient. It had 3 less electrons than it needed. Now it's in a state where it's got 5 less, so it lost 2 electrons. So in a sense, phosphorus could have been oxidized. Now the only problem with this is that nothing else changes. There is no reduction. So what happened to phosphorus was not oxidation. There must be something else going on here that's not an oxidation reduction reaction, because you can't have one without the other. So this is not a redox reaction. Okay? You have to have both for redox. And let's put our great big Sasquatch stamp on this. This time make it a right footprint. There you go, right footnote. There we go. Okay. Here's another one. Let's look at this guy and see if this is redox. Is this redox? Well, let's look at it. Again, real quick here now, oxygen is -2. Don't worry about the 2 in front. It's not going to have any meaning for us. So 2 times 2 is -4, so that makes nitrogen +4. Oxygen is -2 when it's bonded. Hydrogen, therefore, is +1. Oxygen is -2. Hydrogen is +1. Let's do this one in our head, eh? 2 times 2 is -4 plus 1. That's going to be -3. So therefore, nitrogen is going to have to be +3. And likewise with this other guy over here, oxygen is -2. Hydrogen is +1. Again, let's try this one in our head. 3 times 2 is -6. Plus 1 is a -5. So nitrogen has to be a +5 to cancel it out. Is this redox? I got a feeling it is, because nitrogen went from +4 to +3. So it was deficient in 4. Now it's deficient in only 3. That means it must have gained 1. So that was a reduction. Reduction happened to nitrogen. And I'm also looking at this and saying, hey, nitrogen also went from +4 to +5. So this means it was a deficient by 4, and now it's deficient by 5. So it lost another one. So that's an oxidation half reaction. So is this redox? Yes, absolutely. This is a special one. This is disproportionation, remember? Nitrogen is acting as a double agent here. It's being the oxidizing agent and the reducing agent. Okay, there we go. All right. Give some of these a try. Definitely going to see these as multiple choice. They'll give you a compound like dichromate and say, what's the oxidation state of chromium? You have to figure it out, right? 2 plus 3 plus 4 plus 6 plus, something like that. Also, they could give you 4 equations and say which one of the equations is oxidation reduction reaction. And you'd have to assign numbers to each one and see where we had both oxidation and reduction happening at the same time. So give some of these a try. Fire some off at your online tutor. Check the answers in the back of your book. They're good. And see if you can do some of these. And don't forget, go have a look at some of the public exam questions on this and see what ways they ask these questions. All right, I'm going to stop there now. Talk to you later. Bye-bye.